Today we have a very interesting topic, the inertial propulsion mechanism, featured in the free online journal of binary mechanics. Now, the author of the first reference in this article here, Dennis Allen Jr., pointed out that the Boeing Aircraft Company is putting low altitude satellites into orbit using a special inertial propulsion device to levitate it so that it won't fall to Earth. However, it appears that nobody understands exactly how this inertial propulsion phenomena works. That's what this paper is all about. Inertial propulsion may be described as conversion of angular momentum to linear momentum, thus violating Newton's mechanics, in which these momentum types are separately conserved. For example, Eric Lathwaite and others have demonstrated translation motion of a gyroscope only when spinning, called precession, as well as apparent levitation. Unlike Newton's mechanics, the time development laws of binary mechanics do not specifically require separate conservation of angular and linear momentum. However, energy, which are one state bits called quanta in binary mechanics, is conserved. In fact, the time development laws produce quantum motion alternating routinely between circular motion and translation and are the mechanism of inertial propulsion. So let's dive right into it. Figure 1 shows the binary mechanic model of space, which is thought to be a cubic lattice of spot cubes. This whole thing here is the spot cube. The electron spot is shown in yellow, and quanta in the electron spot, there are 6 possible locations for a quanta, tend to rotate in a circle shown by the purple arrows and circle. The black arrows show translation from this circle. As mentioned, this figure shows the spatial object named the spot cube. A cubic lattice of spot cube is the binary mechanics model of space. The spot cube contains 48-bit loci of size L, where L is the primary length constant. There are 2 types of bit locus, M, the white circles, and L, the white arrows. A bit locus may be in the 1 state and energy quanta, or 0 state, in other words, empty. Application of the time development laws of binary mechanics results in circular quantum motion in the electron spot, shown in yellow, shown by the purple circle with arrows. The spin axis, the gray circle in the middle, is a solid diagonal of the spot cube perpendicular to the spin plane. This angular momentum in the electron spot was used in the first ever derivation of Planck's constant from first principles. The time development laws consist of 4-bit operations. When enabled, the strong bit operation captures quanta in the circular motion in the electron spot. When disabled, as described previously, quanta can exit the electron cycle, the black arrows shown in figure 1, by action of the unconditional bit operation. These transitions from circular motion to translation, angular to linear momentum, shown by the black arrows in figure 1, are expressed as 3 p-vectors in table 1. The column sums of the p-vectors is -1, -1, -1, shown here, indicating that the average translation direction is exactly along the spot cube solid diagonal spin axis, suggesting precession away from the electron spot and toward the positron spot, which is on the other side of the spot cube shown in the figure 1 and is therefore not visible in figure 1. Now, if you dare, please join me in looking at the proton-hadron bit cycle, which is much more complicated. The proton-hadron bit cycle was discovered in 2011 and was used in a second derivation of Planck's constant from first principles in 2018. The proton cycle is more complex than the electron cycle. In the schematic here, The same thing we showed you in figure 1, where the yellow path shows the looping motion of quanta in the electron bit cycle, and the same deal. The black arrows show when quanta exit the electron bit cycle. Rather simple compared to all of this other stuff. Notice that the bit locus coordinates omit the commas. For example, 103 up here equals 1 comma 0 comma 3 as the coordinate. Now, there are 6 one-state bit positions in the electron cycle, shown in yellow as we've stated. In the proton bit cycle, there are 42 one-state bit positions. Matter d quarks are the dark red, green, and blue. Antimatter d quarks are the light red, green, and blue. The positron positions are gray. The purple arrows indicate bit motion direction and results of the strong bit operation. As with the electron bit cycle, a quanta in the proton bit cycle returns to its initial position if undisturbed, thereby describing a cycle. This phenomena has been called quanta capture. The proton cycle is the basis for color confinement in particle physics. In the present analysis of inertial propulsion mechanisms, a new phenomena in the proton bit cycle was discovered. Specifically, the orange arrows in figure 2 indicate shortcut transitions from one bit locus in the cycle to another, skipping the normal route following the purple arrows. Now, every change in quanta location in the proton cycle may be viewed as a phase change. Thus, we can define 2 types of phase change. The small changes when following the purple arrow route, which amount to a motion of one primary length constant L per unit time interval. In contrast, the orange arrows indicate a major phase change, also occurring over the same distance in the same time interval, in effect jumping forward within the cycle. Perhaps the major phase changes play a role in inertial propulsion effects. As with the black arrowed translations of quanta exiting the electron spots discussed above, the blue arrows show possible quanta transitions exiting the proton bit cycle. However, as tabulated in Table 2 in the rows highlighted in blue here, there is no net precession direction in these translations. On the other hand, the gray arrows indicate exit from 3 different positron spot units. That is, the column sums of the p-vectors in Table 2 show exactly the opposite precession directions seen in the electron cycle shown above in Table 1. The precession effects may be entirely due to lepton components, the electron or positron. In addition, observed net precession of spinning gyro devices may reflect different probabilities of quanta translation from electrons versus positrons. For example, all else equal, translation from an electron cycle is 7 times more likely than translation from the positron components of the proton cycle, comparing the number of bit locations in each cycle type. Notice the net precession vectors in the proton cycle. The sum of net precession is again along the spin axis, which is the solid diagonal of the spot cube connecting the electron and positron spots, but opposite in sign as shown here. To review, the rows highlighted in orange are the major phase changes discussed above. The rows highlighted in blue are the exit from the proton bit cycle, but there is no net translation there. Like if you add up or sum up just the blue colored rows, you'll find that down here the column sums would be 0, 0, 0. However, we can see that the rows highlighted in gray for the positron spots do show the net precession for the entire proton bit cycle, +1, +1, +1. This report provides further example that the time development laws in binary mechanics produce quantum motion alternating routinely between circular motion in electron and proton bit cycles and translation in quantum motion from one cycle to another. In brief, these laws are the mechanism of inertial propulsion and have precise mathematical definition. Specifically, gyro device precession appears to result from synchronization of circular motion of quanta in multiple bit cycles. The more cycles synchronized, the greater the gyro device size and its precession. The binary mechanic model of space, the spot cube lattice, specifies a fixed direction reference, the bit cycle spin axis. If this anisotropy is confirmed by observations and or experiments in a convincing manner, science would then have an absolute spatial direction reference, something to think about. The Binary Mechanics Lab simulator has been used to demonstrate several translation precession effects evidenced in inertial propulsion devices, which will be in a forthcoming presentation. Keen in preparation. Now the Boeing engineers know why the low altitude satellites put there at low altitude so they can be used in cell phone communications, for example, don't fall to Earth because they have inertial propulsion devices, spinning gyros, to lift them and oppose the effect of gravity.